Okay, so in linear momentum, we learned that the change in P is equal to the force applied times the change in time. And then if we apply that to angular momentum, we can replace force with torque, the torque applied, times the change in T, or change in time, and we can assume that that's a true statement. Torque is equal to the force times, or cross multiplied by the distance from the pivot. But when we're looking at an orbit like this, or we can just put it where it is, right? Then the force applied, Fg, is going inward, and the distance from the pivot, from this mass, is r. Those two are parallel to each other, which means that these two cannot be perpendicularly multiplied. So that means that torque has to equal to 0. And if torque equals to 0, we plug that into here, then the change in angular momentum is also 0. So by that, we can assume that the initial angular momentum is the same as the final angular momentum. So the angular momentum of the perigee is equal to the angular momentum at the apogee. And then we can expand this to CMVR. Wait. And then the constant is just 1 because we're treating it as a point mass. And then the masses cancel out because it's the same mass. And this is our final equation. Okay, so in this ellipse orbit, as the comet is orbiting the sun, there's no motor pushing it forward or pushing it back, and there's no drag. The only force acting on it is F of g. So we can assume, because there's no external force being applied to the comet in orbit, that the mechanical energy is conserved from every point, including from the points of the perigee and from the apogee. Okay, we can also visualize it like this, where if we cut up this ellipse into areas, we want all these areas to be equal, meaning that the bigger this distance is, the bigger or the smaller this distance covered has to be in the same amount of time. So this would be V of A, right? These areas are equal. So again, let me reiterate that this smaller distance from the sun equates to a larger orbital speed. So if the r of the perigee is less than the r of the apogee, then the v of the perigee is greater than the v of the apogee. The general formula is kinetic energy plus potential energy, or also 1/2 mv squared minus g times the mass of the sun times the mass of the comet over the distance. So if we take this and then apply it to the perigee and then the apogee, we'll get this. And then in all of these terms, the little mass cancels out. So we're left with this equation for the conservation of energy. Sorry, this is an awfully drawn R. That's an R, not a V. Okay. This is my final equation. Okay, so for part C, I'm going to use this equation that you gave us, or that I derived from part A. And then in the final equation that you want me to prove, there we have the terms VP in it, VA, and RA. So what we don't have is RP, so I'm going to isolate for this so we can replace it. And then I'm going to plug that into this equation for RP. So, and then I can just bring the VP to the top. Okay, and what I see is this common 2 in the denominator. So I'm going to move that over, and I actually see this RA in the denominator, so I'm going to try to combine those terms by subtracting this over and then adding this over. So I'm going to take out the 1/2 as I add this over, or subtract this over, sorry. And then I'm going to do this GM VP over VA. And then subtract GM over RA, except I want this common denominator, so I'm going to multiply this by VA over VA. And then what I can do on this side again is expand this to VP plus VA times VP minus VA. Because these are basically the same thing. Okay? And then I see a common constant here, GM, which I'm going to take out because I can. And then I can also take out VA times RA because we had that as a common denominator. And then VP minus VA. Okay, and what I'm seeing here is that this term cancels with this term, so let's rewrite it. 1/2 times VP. Actually, I'm going to expand this. Equals to GM VA RA. And I want to isolate for VP, so I'm going to subtract this over to the other side. And then multiply both sides by 2. Okay. And since in the FRQ you gave the mass of the sun a subscript, I'm just going to add it to all of the masses of the sun so that I don't get my points docked off. Okay. Beautiful. Okay, so in part A, we solved for this equation. And I want to isolate for VP because in the last part C, we also solved for this equation. So because these are both equal to each other, I'm going to set them as equal to each other. And then they actually give us most of these values. So they give us RA, RP, G, the mass of the sun, and this RA. So we can isolate for VA. And then I'm going to add this VA over. Okay, and then I'm going to take the VA out on this side. And then if I solve for the left side, it'll give me about this value. And then I'm gonna multiply this up. So this value times this value. And then this would expand to be about and then times VA squared is equal to, and then I can isolate for the orbital speed of the apogee here. And as my final answer, I'll get 5,822.196. Okay, and then we can solve for VP by plugging this equation in. And I got meters per second. So this is the orbital speed of the apogee, and then this is the orbital speed of the perigee. Which makes sense, right? Because we earlier said that the speed of the perigee has to be greater than the speed of the apogee. So, yes. Okay, so we know that the mechanical energy equals to kinetic energy plus potential energy, which is also this. And then we also know that mechanical energy equals to this in the case of an ellipse. So since these are both mechanical energy, we can set them as equal to each other. So 1/2. So our goal here is to isolate for V. So I'm just going to do algebra now. Cancel out this little m. And then I'm going to add this term over. And then I'm going to multiply this both sides by 2. These 2's cancel out. And then I'm going to square root both sides. And then we can take out the g and then the mass of the sun out because we can. It's a common factor in both. And then I'm going to keep this 2 on the side because it's positive here and then it's negative here. So minus 1 over a. Okay, so for part F, we can set FC as equal to FG in a circular orbit and then expand that. And then here we can cancel out the little m and then the little r. And then we can square root both sides to isolate for V. And in this case, this would be V naught. And then on the other hand, we already solved for this equation here. And then instead of A. Here, I'm just going to rewrite this as this. And then I'm going to solve for these because we're already given the values. So oh, I forgot the subscript. Okay, and then we're given this as an answer. Okay, and then for VP, we can plug in all these values as well. And then we're given this value. And then if we compare these two, so we end up with VP in the elliptical orbit is greater than the orbital speed of the circular orbit. Or this new V naught is less than the original VP of the elliptical orbit.